Welcome you in the lecture series of random processes, detection and estimation. It is 47th lecture of this series. In the previous lecture we have discussed dynamical signal model and scalar Kalman filter. In this lecture we will continue our discussion with Kalman filters. The outline of this lecture are scalar vector, scalar observation, Vector Kalman filter, and in the objective of this lecture you will able to explain what is the Vector Kalman filter. Now first we consider scalar vector scalar observation. Consider the scalar state equation and the scalar observation equation. Sn is equal to a Sn minus 1 plus omega when n. It is the scalar state equation, and the scalar observation equation Sxn is equal to Sn plus omega n, where omega 1 and omega n are the zero mean Gaussian noise with independent samples and having the expected value E omega square n. It will be equal to sigma omega square, where S minus 1, omega 1 n and omega n are all independent, and let S minus 1 is the normal random process with mean mu s and variance sigma s square. We want to estimate Sn based on the observations x0, x1 to xn, or to filter xn to produce x cap n. Our criteria of optimality will be the minimum Bayesian MSE, or the expected value of the whole square Sn minus S cap n by n. Here Sn by n, it is the expected value of Sn into x0, x1 to xn, or x cap n by n, it is the cross covariance C theta x into autocovariance C xx inverse into x. Since theta is equal to Sn, then x is equal to transpose of x0 to xn, and these are jointly Gaussian. Theta and x are jointly Gaussian. If xn is uncorrelated with x0, x1 to xn minus 1, then S cap n by n, it will be the expected value of Sn into x0, x1 to xn minus 1 plus expected value of Sn xn. So we can write it as S cap n by n, it is the S cap n by n minus 1 plus expected value of Sn plus Sn into xn. And this is the desired sequential form. Using the property of MMSE estimator, theta cap will be the expected value of theta given x1, x2, and it will be the expected value of theta theta by x1, means the conditional expected value of theta when x1 is given, plus conditional expected value of theta when x2 is given. If theta is zero mean, means MMSE estimator is additive. If theta 1 is equal to theta 1 plus theta, if theta is equal to theta 1 plus theta 2, so theta cap is equal to conditional expected value E theta by x is equal to conditional expected value theta 1 plus theta 2 when x is given, and you can write it as expected value of theta 1 when x is given plus expected value of theta 2 when x is given. So x cap n by n, it will be S cap n by n minus 1 plus expected value of Sn and xn bar, and S cap n minus n by n minus 1, it will be a S cap n minus 1 given n minus 1, and the expected value of Sn x bar n, it will be kn x bar n, and where kn, this kn is the gain factor or Kalman gain, and kn can be written as mn by n minus 1 divided by sigma n square plus m n when n minus 1 is given n by n minus 1. So here n by n minus 1 means n given n minus 1. This is the expected value of whole square of Sn minus S cap n by n minus 1. And this is mn by n minus 1. It is the minimum prediction of MSE. Now Vector Kalman filter. Let Sn is equal to a Sn minus 1 plus b omega n. These are in vector form, where n is greater than equal to 0, and A matrix is the P is to P matrix, and B is the P into R matrix, and omega n is the vector of white Gaussian noise with the mean 0 and covariance theta. And S minus 1 is the normal process with mean mu s and covariance Cs, and S minus 1 is independent of omega n's. Now for nth data sample, xn is equal to H transpose n Sn plus omega 1 n. Here xn is p is to 1 vector, and omega 1 is zero mean Gaussian noise with uncorrelated samples with variance sigma n square. Now the prediction is S cap n by n minus 1. It will be A S cap n minus 1 by n minus 1. The minimum prediction MSC matrix, that is P by P matrix, it will be M n by n minus 1. It will be A m n minus n given n minus n A transpose plus B Q B transpose. The Kalman gain vector Kn is equal to m n by n minus 1 Hn divided by x n square plus H transpose x m n by n minus 1 Hn. So this is the end of this lecture. In this lecture series of random processes, lectures were divided into developing backgrounds in the area of random processes representation, detection and estimation theory. We have discussed the representation of random process, and we have also discussed the hypothesis testing for Bayes and Neyman-Pearson criteria. The fundamentals role of the likelihood ratio was developed. The simplest problem was that of detecting one of two known signals in presence of additive white Gaussian noise. The matched filter receiver was first important result. Turning to estimation theory, we studied Bayes estimation for the random parameters and maximum likelihood estimation for non-random parameters. The idea of likelihood functions, efficient estimates, and the Kramer-Rao inequalities were of the central importance in this discussion. The close relation between detection and estimation theory was emphasized in the composite hypothesis testing problem. The idea of linear estimation and non-linear estimation of parameters were derived. The matched filter for dealing with unwanted parameters such as a random amplitude or random phase angle was derived. In this lecture series, we try to deal with all basics of signal detection and signal parameter estimation. So thanks for listening this lecture series. Thank you.